Mr. Chair and co-chair of the session, dear colleagues, guests, participants, Assalamu alaikum. Good morning. At first, I would like to thank the organizing committee for inviting me to deliver a talk in this great conference. The topic of the talk is just the origin of segregation in liquid metallic binary alloys. And so I'll spend 20 minutes on this topic. Now, let us move to the second slide. The outline of the talk is just the introduction, theories. That means I divided my talk into 4 parts. So one is introduction, theories, results, and discussion and conclusion. Okay, the third slide. So introduction. In the introduction, I have 3 questions. What is segregation or phase separation? Why does it happen? What is critical exponent related to phase separation or segregation? So I'll talk one by one. On the first question. What is segregation or phase separation? At the beginning, if you look to the left figure, we see the 2 tubes. One is at 25 degrees Celsius, another is 4 degrees Celsius. So at 25 degrees Celsius, you see the 2 components of the mixture looks alike. There is apparently there is no distinction between them. But on the right, at 4 degrees Celsius, if you look at the tube, we see the 2 liquids are now separated from each other. And so segregation happened here. And from the molecular level of description, if you look to the right figure, we can see, it's the low temperature region and it's the high temperature region according to the arrow of the T. So at the high temperature region, you see the red and white molecules are mixed uniformly, almost uniformly there. And if we reduce the temperature, then the white molecules going up and the red molecules are going down. And after further reduction of temperature, all white molecules went up and the red molecules down. So here the complete phase separation or segregation or phase transition, whatever you call it. And then now what is the actually the segregation? Segregation is the property in which the component of the mixture and starts or begins to separate from each other. After complete separation, we call it phase separation. Now the question is, are all metallic alloys suffer from segregation? No, there are very few alloys among thousands of alloys, and that obey the segregating properties or segregating law. Some of them are mentioned below. You see the bismuth zinc, lead zinc, and this and this. So the alloy in the zinc is my sample for presentation, and most of my talk I will give on this alloy and later generalize. Okay, now let us go to the second questions of the introduction. Why does phase separation happen? It is a good question, but it is not completely understood from the microscopic point of view. Still now, although we have advanced so far for understanding this. Now, let me try to find the cause why phase separation happens from the point of thermodynamics. From the point of thermodynamics, and there are other ways to describe the cause, but from the point of thermodynamics, you see in the left figure we have plotted the free energy as a function of volume, and in the case of liquid gas phase separation. So when we look at the free energy, you see the free energy is decreasing, and then after a certain point, it increases and then again decreases and again minimum. So there are two minima here, one at point 1.2. So, and in between the free energy increases. But thermodynamics says that for equilibrium state, the energy must be minimum for the system. So it is clear from here that the gas, liquid and gas, you see the left on the left side of D, that is in the one region, the liquid is at equilibrium, and on the right side, gas is in equilibrium. But here there is a barrier, and this barrier is the free energy barrier, from which separates the two states, the two components here in the phase separation. And let us see at the different phenomena, magnetism. In the case of magnetism, you see the ferro to para. If we calculate the free energy, you see here it is the AB mixture. The percentage of B is increasing in this way. If you look at, you see the similar behavior of the free energy. It is coming down and goes to a minimum, and then it increases and goes down and again increases. So again here, according to thermodynamics, this is the equilibrium state. This is another equilibrium state. So in this state, the magnetism is at equilibrium, and on the other side, paramagnetism is there. So there is a phase separation, and here particularly we call it the phase transition from ferro to para. And the reason is the sudden harm of the free energy curve, and which actually indicates the disturbance or instability, and which causes the separation of the phases. Now, in the next slide, if you look, the free energy of a liquid-liquid binary element, that a liquid-liquid phase separation, which is my subject to speak on. Here you see the same picture. If you look at this curve at 1000 degree Kelvin for copper cobalt binary alloys, you see the free energy is here minimum, and then that means it is free energy of mixing minimum and goes up and come to the minimum. So here is the free energy minimum. Equilibrium state is found here. Equilibrium state is found here, but in between there is no equilibrium state. So segregation happens. So here the cobalt, particularly in this concentration, on the left of this concentration, you will find the copper at equilibrium state, and here cobalt. So there is no mixture of the cobalt and cobalt here in this concentration, around this concentration. So from the point of free energy, or from the point of thermodynamics, we can see the different physical phenomena: liquid, gas phase transition, ferro para phase transition, liquid-liquid phase separation, all behave in the similar way when we look from the aspect of the free energy of the system. Now let us move to the second question. Now, third question of the introduction. In the introduction, we have a third question. What is critical exponent? You have heard the name of the critical behavior of the system and many things. And what is critical exponent and what is critical behavior? To understand it clearly, we look at two different phenomena here. You see the liquid to gas phase transition when we increase the temperature. Okay, and it is different phenomena. It's a ferromagnetism to paramagnetism. Here there is a magnetic ordering, and in the paramagnetism, when we increase the temperature, there is no ordering, and there is a certain temperature. This is called the critical temperature or transition temperature, or in ferromagnetic we especially call it the Curie temperature, and there is certain temperature after which we find the paramagnetism, and before that is ferromagnetism. So totally different phenomena. But if we look at the specific heat at constant pressure, you see, if we look at the specific heat for liquid gas phase transition, we see that at the specific heat increases, and it diverges. It diverges at critical temperature, Tc. Again, if you look at the magnetism as a different thing, the ferro to paraphase separation, you see when it comes to the critical temperature, that means Curie temperature, and the specific heat, here there is a divergence of the specific heat. So very interesting thing, two different phenomena, but behaving similarly, particularly at the critical point. So we can assume that, so the critical phenomena does not depend on the material or type of materials we are using, but there is a generality or universality in this behavior, particularly near the critical point. And another thing I would like to mention that physics has been developed too much, but still now we do not know what happens at the critical temperature. But what we can explain with the present theory or renormalization group theory, that what happens very close to the critical point. But what happens at the critical point is not known to us. Now, let me see the what is critical exponent. And if you look at the liquid gas phase separation, here is the picture for liquid gas phase separation. Here you see the density of the liquid minus density of the gas very close to the critical point, not Tc. If it is T is Tc, then it is zero. There is no information from the at the critical point. So very close to the critical point, you see it behaves like a power law. You say there is a power here 0.327. It is found, and it is a completely different phenomenon, in which you look magnetization near the critical point is T minus Tc power 0.311. And these both are experimental data I have placed here, experimental data. Now it is too much interesting that all the different phenomena, one is liquid gas phase transition, another is paraferro phase transition, but at the critical point, they are behaving in the similar way. You see, the exponent is very close to each other. That means within the experimental error, these are the same exponent. So this is the most interesting thing in the critical phenomena, and the exponent is known as the critical exponent, what I was talking about. Now, if we look about in the that means magnetic susceptibility, you see from the theory, if there are students in the audience, they in the fourth year or third year solid-state physics, they study the magnetism and particularly mean field theory, which they call the Curie-Weiss law. And from the Curie-Weiss law, they see that chi magnetic susceptibility is following a exponent -1. That means they find that C divided by T minus Tc it is very close to the transition point. And what experimentally happens, if experimentally it is not the -1, the exponent is -1.33. So we can now distinguish between the mean field theory and the real behavior of the magnetic systems. So these are the two things. Now, one thing I would like to say, I'd like to tell you that there is a term called universality. What is universality? You say if different phenomena, but if at the critical point or the critical about transition point, if their exponent is similar, so they belong to the same universality class. And if there is a different exponent for different values, different phenomena at the critical point, then they belong to a different universality class. And how the universality class is defined by using actually the dimension from the dimension that which belong to which universal class. So now we have understood what was the critical temperature and why it appears and its universal behavior for different physical phenomena at the critical temperature. And we see that here some distinction between what we have learned in the third year, fourth year honors class from the solid-state mathematics is just mean field theory and how it deviates from the real behavior of the susceptibility. Okay, now let us go to so our three questions is answered already, which we mentioned in the introduction. Now, in our case, in the liquid binary alloys, to study the segregation, we have used both the thermodynamic way and the dynamic way. The thermodynamic way, we use the thermodynamic properties, that is the free energy or free energy of mixing. So at the beginning, you see how we define different thermodynamic functions. We know in thermodynamics there are 4 variables. 2 are mechanical variables. P and V are.
Sir, you have 2 more minutes.
Oh, really? So okay. So this is the thermodynamic I shall use as a proof to describe the things. So, and we use the perturbation theory. We use the electron-ion interaction. That means electronic theory of metals. And these are the hard-spell liquid expressions and the structure-dependent part of this. And now, if I say few things on the results and discussions. And now this is my system, aluminum bismuth, as I told you. Here the breakdown. You see the reference system, the free energy of mixing of the reference system is the blue one and that one. And we calculated at this temperature because some experimental data are available here. So we see to check the approach we are using, how accurate it is. So just to display that, we have presented this figure. We see we can reproduce, but the theory we have used can reproduce the experimental data in the liquid state. Okay, so we now assume that the theory is accurate and good. Now here, if you look at the energy of mixing at different temperature, you see at high temperature, this is the curve for energy of mixing. It is liquid forward. That means that indicates the mixing state. When we reduce the temperature, you see there is a hump in the energy curve, and so the segregation appears or phase separation starts from here. And the beginning, the concentration at which it begins is known as the critical concentration, and the temperature it begins is known as the critical temperature. And you see the concentration gap increases as the temperature is reduced. Then you see the enthalpy of mixing, similar phenomena. Here we have some experimental data as well, so that fit very well at different temperature. Now this is the entropy of mixing. We have used the whole three, the energy of mixing, entropy of mixing, and enthalpy of mixing, but they are related thermodynamically. And when we treat them separately, we can be sure that our theory is working well. So this is the behavior from 3 different thermodynamic properties, but the segregating behavior here is shown spectacularly from this figure. Now, if you look at a glance, you see the critical properties we have started so far for different alloys. You can see these are the critical concentrations we have.
Sorry, sir, your time is over.
Experimental values. These are the critical concentration, critical temperature, and these are the corresponding experimental values. And here the critical exponent, as I told you, we have calculated the viscosity, and from the viscosity is related to that. This beta is a critical exponent, and beta is equal to, we have found from this log curve is 1.08 for segregation of our system. And for liquid gas system, it has a different value. But when you look at the gelatin, you see that at the gel point, we see that beta these are the scattered data of experimental scattered data. So within this data, 1.08 lies. So I can say that the segregation of the aluminum bismuth binary alloys maybe lie in the same university class at the gelatin. You see in the lower figure, the gels are seen. There are some experimentalists who use the soul gel experiment. So this is the gel. So now these are the concluding remarks. And the third one, I just said that the critical exponent for viscosity in the case of the segregation is of the same order of magnitude of the gel at the melting point. So they form a different universality class. And that's all from me. And these are our recent publications. And thank you for your kind attention. Thank you very much.